You think electricity flows through wires like water through pipes. Everyone does. It's how we're taught. Current flows from the battery, through the wire, to the light bulb. Simple. Intuitive. Makes perfect sense. Wrong. Completely. Fundamentally wrong. And Richard Feynman knew this. He spent years trying to get people to understand what electricity actually is. Not the sanitized textbook version. Not the simplified model they teach in schools. The real thing. The thing that's actually happening when you flip a light switch. What he found was so strange, so counterintuitive, that most people refuse to believe it even when you show them the math. Even when you demonstrate it experimentally. Even when you prove it beyond any reasonable doubt. Let me show you what I mean. Here's a simple question. You have a light bulb connected to a battery with 2 wires, 1 meter of wire on each side. You flip the switch. How long does it take for the light to turn on? Most people say instantly, or they say the speed of light. The sophisticated ones calculate how long it takes electrons to travel 1 meter at their drift velocity, which is about a millimeter per second. So they say roughly 1,000 seconds, about 16 minutes. All wrong. The answer is approximately 3 nanoseconds, 3 billionths of a second. The light turns on almost instantly, but not quite. There's a tiny delay, and that delay is not because electrons are traveling through the wire. That's not what's happening at all. Stop right there. Rewind. Let's start with what you think you know. You learned in school that electricity is the flow of electrons, that when you connect a battery to a wire, electrons flow from the negative terminal through the wire to the positive terminal. And that flow of electrons is what we call electric current. That's not wrong exactly. Electrons do flow. But here's what they don't tell you. Those electrons are moving incredibly, unbelievably slowly, about 1 millimeter per second. At that speed, if you had a wire stretching from your house to the power plant 10 miles away, it would take the electrons about 6 months to make the trip. 6 months. But when you flip a light switch, the light comes on instantly. Not in 6 months. Right now. Immediately. So what's actually happening? Feynman explained it this way. The wire is already full of electrons. Completely packed. Copper has about 1 free electron per atom, and there are roughly 10 to the power of 22 atoms per cubic centimeter. That's 10 billion trillion electrons just sitting there in every cubic centimeter of wire, ready to move. When you close the switch, you don't wait for electrons from the battery to travel to the light bulb. The electrons already at the light bulb start moving immediately, or almost immediately, because what travels through the wire is not electrons. What travels is a signal, an electromagnetic wave, a disturbance in the electromagnetic field, and that wave travels at nearly the speed of light. Think of it like a pipe completely filled with water. The pipe stretches across the room. You push water into one end. What happens at the other end? Water comes out immediately. Not because the water molecules you push travel the length of the pipe, but because the push propagated through the water as a pressure wave. The water at the far end was already there. It just needed to be told to move. That's electricity. The wire is full of electrons. The battery creates an electromagnetic field. That field propagates through and around the wire at nearly light speed. The field tells the electrons to move. They move. The light turns on. But here's where it gets really strange. Here's the part that Feynman spent years trying to get people to understand. The energy doesn't travel through the wire. Read that again. The energy that powers your light bulb does not travel through the wire. It travels through the space around the wire, through the electromagnetic field surrounding the wire. The wire is just there to guide the field, to shape it, to tell it where to go. But the energy, the actual power that makes the bulb light up, that's traveling through empty space, this is not a metaphor. This is not a simplification. This is literally, actually, physically what happens. Feynman used to demonstrate this with a thought experiment. Imagine 2 parallel wires stretching across the universe, miles apart, light years apart, doesn't matter. Now connect them to a battery on one end and a light bulb on the other end, forming a giant rectangular circuit. The circuit is enormous. The wires are absurdly long. You flip the switch. How long until the light turns on? If energy traveled through the wire, you'd have to wait for the signal to go all the way around the circuit. If the wires are a light year long, you'd wait 2 years for the light to turn on. But that's not what happens. The light turns on almost immediately. In the time it takes light to travel straight across from the battery to the bulb, not around the circuit, straight across, because the energy doesn't go through the wires. It goes through the space between them. The electromagnetic field forms between the two wires, and energy flows through that field, through empty space from the battery to the bulb. The pointing vector, that's the technical term. It describes the flow of electromagnetic energy. And if you calculate the pointing vector for a simple circuit, you find something shocking. The energy flows perpendicular to the wires. It flows in the space around and between the conductors, not through them. The wires are just there to create the electric and magnetic fields. The fields interact and energy flows through the field. The wires guide the energy like guardrails on a highway, but the energy isn't traveling in the guardrails. It's traveling in the space they define. This should break your brain. Everything you thought you knew about circuits is wrong, or at least incomplete, deeply incomplete. Feynman loved this. He loved finding these places where the textbook explanation was technically correct, but completely missed the deeper reality, where the simplified model led people to visualize something that wasn't happening. He used to say, "I think I can safely say that nobody understands quantum mechanics." But he could have said the same thing about electricity. Nobody really understands electricity. They understand the simplified models. They can calculate voltages and currents and resistances, but they don't understand what's actually happening. They don't see the fields. Let's go deeper. Let's talk about what an electromagnetic field actually is. You've probably heard the term a million times. Electromagnetic field. Electric field. Magnetic field. But what does it mean? What is a field? Here's how most people think about it. A field is a mathematical description. It's a number you assign to every point in space. The electric field at this location is 100 volts per meter. The magnetic field at that location is 0.5 Tesla. It's just a map, a way of organizing information. Wrong, or at least that's not what Feynman thought. And he was right. A field is real. It's physical. It exists. It has energy. It has momentum. It can do work. The electromagnetic field is not a mathematical description of how charged particles interact. The electromagnetic field is the thing doing the interacting. When you bring two magnets together and feel them push or pull, what are you feeling? You're not feeling the magnets acting on each other. You're feeling the magnetic field. The field is real. It's there in the space between the magnets, pushing them apart or pulling them together. Feynman was obsessed with this. He spent years developing a completely different way of thinking about electromagnetism, where the field was the fundamental thing and particles were just disturbances in the field. Most physicists didn't want to think this way. It was too strange, too different from the classical picture. But Feynman insisted because he understood something deep. The field is not a convenience. It's not a mathematical trick. It's reality. And once you understand that the field is real, everything changes. Electricity is not electrons flowing. Electricity is an electromagnetic field propagating through space, pushing electrons around as a side effect. The electrons are just markers. They show you where the field is strong. But the field is the thing that matters. The field is carrying the energy. The field is doing the work. Now let's connect this to something you can actually see. Radio waves. You have a radio transmitter. You have a radio receiver. The transmitter sends out radio waves. The receiver picks them up. How? The standard explanation is that the transmitter creates electromagnetic waves that propagate through space at the speed of light. The waves reach the receiver and the receiver detects them. Simple. But what's actually happening? What is the radio wave? It's not a thing. It's not a particle flying through space. It's a disturbance in the electromagnetic field. The transmitter shakes the field. That shaking propagates outward in all directions at the speed of light. When the disturbance reaches the receiver, the field at that location is shaking. The receiver detects the shaking. That's it. The electromagnetic field permeates all of space, always, everywhere. The radio wave is just a ripple in that field, a wave moving through the medium. Except the medium isn't air or water. The medium is the field itself. And here's the thing that should make you stop and think. When you flip a light switch in your house, you're doing the same thing. You're creating a disturbance in the electromagnetic field. That disturbance propagates through the field at nearly the speed of light. The disturbance reaches the light bulb a few meters away in nanoseconds. The field at the light bulb location is now different. The electrons in the light bulb respond to that field. They move. The filament heats up. The light turns on. Radio waves and electrical circuits are the same phenomenon. They're both electromagnetic waves propagating through the field. The only difference is frequency and geometry. A radio wave is a high-frequency oscillation propagating through open space. An electrical signal in a wire is a lower frequency disturbance propagating through a guided geometry. But it's the same physics, the same fields, the same waves. Feynman understood this deeply. He saw the unity. He saw that all of electromagnetism is really just one thing, the electromagnetic field. Everything else, all the circuits and antennas and motors and generators, they're just ways of manipulating that field. Let me tell you a story. In the 1940s, Feynman was working on the Manhattan Project. He was thinking about electromagnetic theory, trying to understand it at the deepest level, and he realized something strange. The standard formulation of electromagnetism, Maxwell's equations, they describe how fields create other fields, how changing electric fields create magnetic fields and vice versa. But they don't explain where the fields come from in the first place. They don't explain the source. So Feynman developed a different approach. Instead of thinking about fields, he thought about how charged particles interact with each other directly. One electron sends out a signal. That signal travels at the speed of light. When it reaches another electron, the second electron responds. Direct action at a distance, or rather direct action with a time delay. He called it the absorber theory. He worked on it with his advisor, John Wheeler, and they found something remarkable. If you assume that every charged particle in the universe is interacting with every other charged particle, sending out signals forward and backward in time, and you add up all the interactions, you get exactly the same predictions as Maxwell's equations. The electromagnetic field emerges from the interactions. It's not fundamental. It's a consequence. Now, this approach didn't win. Most physicists stuck with the field. Picture, because it's easier to work with. But Feynman never forgot what he learned. The electromagnetic field might be the most convenient way to think about electricity and magnetism, but it's not the only way. And understanding that there are multiple ways to think about the same phenomenon, that's what gives you deep insight. Here's another thing most people get wrong about electricity. They think voltage is what makes things happen. High voltage is dangerous. Low voltage is safe. That's why we use high voltage power lines and low voltage batteries, but that's not quite right. Voltage doesn't kill you. Current kills you. Specifically, current flowing through your heart. It only takes about 100 milliamps across your heart to cause fibrillation and death. That's a tenth of an amp. Your phone charger can supply more current than that. So why don't you die when you touch your phone charger? Because your skin has high resistance. The voltage isn't high enough to push significant current through your skin and into your body. You need thousands of volts to overcome that resistance. But if your skin is wet, if you're sweating or standing in water, the resistance drops. Now even 120 volts household electricity can push enough current through your body to kill you. The voltage didn't change. Your resistance changed, and it's the current that matters. Feynman used to emphasize this point. Voltage and current are not the same thing. Voltage is the push. Current is the flow. You can have high voltage with no current if there's no path for the current to flow. And you can have high current with low voltage if the resistance is low. What matters for doing work, for delivering power, is the product of voltage and current. Power equals voltage times current. That's why the power grid uses high voltage. It reduces the current for a given amount of power, which reduces energy loss in the wires. The wires have resistance, and when current flows through resistance, energy is dissipated as heat. That's wasted energy. By using high voltage, you can transmit the same power with less current, which means less loss. But again, this is thinking in terms of current flowing through wires, and we've already established that's not really what's happening. The energy is flowing through the field around the wires. The current in the wires is just a consequence of the field. It's a side effect. So what's really happening in the power grid? The power plant generates an alternating electromagnetic field. That field propagates through the space surrounding the transmission lines at nearly the speed of light. The field carries energy from the power plant to your house. When the field reaches your house, it induces currents in your wiring. Those currents power your devices. The transmission lines are just there to guide the field, to give it a path to follow, to keep it contained and directed. But the energy is not traveling through the metal. It's traveling through the air and the insulation surrounding the metal. This has practical consequences. If you want to transmit power efficiently, you need to think about the field, not just the current. The geometry matters. The spacing between wires matters. The materials surrounding the wires matter, because all of these things affect how the field propagates, and the field is what's carrying the energy. Let's talk about one more thing, inductance. You probably learned about inductors in school. A coil of wire that resists changes in current. When you try to increase the current, the inductor fights back. When you try to decrease the current, the inductor tries to keep it flowing. They're used in filters, in power supplies, in radio circuits. But why do inductors work? The standard explanation is Lenz's law. A changing current creates a changing magnetic field. The changing magnetic field induces a voltage that opposes the change in current. That's true. That's correct. But it doesn't explain what's actually happening. Here's what's actually happening. When current flows through a wire, it creates a magnetic field around the wire. That field stores energy. When you increase the current, you're putting more energy into the field. That energy has to come from somewhere. It comes from the source driving the current. The source has to do work against the magnetic field to increase the current. That's what you feel as resistance to change. Similarly, when you try to decrease the current, you're taking energy out of the magnetic field. But that energy has to go somewhere. It goes into maintaining the current. The field releases its stored energy, keeping the current flowing even as you try to stop it. An inductor is an energy storage device. It stores energy in the magnetic field. And because it takes time to move energy into or out of the field, inductors resist rapid changes in current. This is not just an analogy. The magnetic field literally contains energy. You can calculate how much. The energy density is proportional to the square of the magnetic field strength. If you integrate that energy density over all space, you get the total energy stored in the field. For a typical inductor, it's a tiny amount, millijoules or microjoules, but it's real energy really stored in the field, really sitting there in the space around the coil. Feynman would draw pictures of this. He'd sketch the field lines, show how they loop around the wire, point out where the energy is concentrated. He wanted people to visualize the field, to see it as a real physical thing with structure and energy and dynamics. Because once you see the field, once you understand that it's real, everything makes sense. Inductors make sense. Capacitors make sense. Transmission lines make sense. Antennas make sense. It all comes together into one coherent picture. Electricity is not electrons flowing through wires. Electricity is electromagnetic fields propagating through space, and we've learned to guide and manipulate those fields to do useful work. The electrons are just along for the ride. Now here's where it gets really mind-bending. Let's talk about what happens when you disconnect a circuit. You have a long cable, maybe 300 meters long, connected to a battery on one end and a light bulb on the other end. The circuit is closed, current is flowing, the light is on. Now you cut the wire somewhere in the middle. What happens? The obvious answer is the light goes out immediately. No more current flowing, no more light, right? Wrong. The light stays on for about 2 microseconds, 2 millionths of a second. Then it goes out. Why? Because when you cut the wire, you don't instantly stop the electromagnetic field. The field is real. It has momentum. It has energy. It's propagating through space at a finite speed. When you cut the wire, you create a discontinuity in the field. That discontinuity propagates along the wire at the speed of light. It takes time to reach the light bulb. Until it arrives, the field at the light bulb hasn't changed. The electrons at the light bulb don't know the wire has been cut. They keep moving. The light stays on. For 300 meters at the speed of light, that's about 1 microsecond to the cut point and 1 microsecond back to the bulb. 2 microseconds total. Then the disturbance arrives. The field collapses. The current stops. The light goes out. This has been measured. It's real. You can do this experiment and observe the delay. The light doesn't go out instantly. It goes out after a propagation delay determined by the speed of light and the geometry of the circuit. This is not intuitive. This is not what anyone expects. But it's what happens. Because the energy is in the field, not in the current. And the field takes time to change. Feynman loved these kinds of examples. He loved showing people that the universe is stranger than they imagine, that their intuitions are wrong, that they need to think more carefully about what's actually happening. And this brings us to the deepest point, the thing Feynman spent his whole career trying to understand. What is the electromagnetic field, really? Not how do we calculate it, not what equations describe it, but what is it physically, ontologically? What is this thing that permeates all of space, carries energy and momentum, can push electrons around, can propagate at the speed of light? The answer ultimately is quantum field theory. The electromagnetic field is a quantum field. It's not a classical field. At the deepest level, the field is made of photons, virtual photons popping in and out of existence, mediating the electromagnetic force. When an electron interacts with another electron, they exchange virtual photons. Those photons are the field. The field is quantized granular, made of discrete chunks. But even saying it's made of photons is not quite right, because photons aren't little particles. They're excitations of the field, ripples, disturbances. The field is the fundamental thing, and particles are just patterns in the field. Feynman developed quantum electrodynamics, QED, to describe this. It's the most accurate theory in all of physics. Predictions match experiments to 10 decimal places. It's been tested over and over and over, and it always works. Always. QED tells us that the electromagnetic field is real, quantum, and fundamental. Everything else, all the electricity and magnetism and light and radio waves, they're all manifestations of this one quantum field interacting with charged particles. And here's the thing that should completely restructure how you see reality. When you flip a light switch, you're manipulating a quantum field. You're creating disturbances in that field. Those disturbances propagate at the speed of light. They reach your light bulb. They cause electrons in the filament to accelerate. The accelerating electrons radiate photons. Those photons enter your eyes, and you see light. Every step involves quantum fields, the electromagnetic field propagating, electrons responding to the field, photons being emitted and absorbed. It's all quantum mechanics all the way down. But here's the beautiful part. You don't need to understand quantum field theory to use electricity. You don't need to visualize virtual photons to design a circuit. The classical approximation works perfectly well for almost everything. Maxwell's equations, Ohm's law, Kirchhoff's laws, they all work. They give you the right answers. But they don't tell you what's really happening. And Feynman thought that was important. He thought people should know what's really happening. Not just the equations, not just the calculations, but the physical reality, the fields, the photons, the quantum nature of everything. Because once you know that, once you see the world that way, you can't unsee it. You look at a light switch and you see quantum fields. You look at a wire and you see electromagnetic waves. You look at a radio and you see disturbances propagating through space at the speed of light. The universe is not made of stuff. It's made of fields, quantum fields, the electromagnetic field, the electron field, the quark fields, all interpenetrating, all interacting, all creating the reality we experience. Particles are just excitations of these fields. Forces are just fields interacting. Everything, and I mean everything, is fields. Electricity is not electrons flowing through wires. Electricity is a quantum electromagnetic field propagating through space, interacting with matter, doing work, transferring energy. And we've learned to control that field, to guide it, to use it to power our civilization. That's what Feynman understood. That's what he spent his life trying to explain. The universe is made of fields, and if you want to understand electricity, really understand it, you have to understand the fields. Not as mathematical abstractions, not as calculational tools, but as physical reality. The next time you flip a light switch, remember what's actually happening. You're not completing a circuit. You're not sending electrons through a wire. You're creating a disturbance in the electromagnetic field. That disturbance propagates through space at nearly the speed of light. It reaches the light bulb in nanoseconds. The field at the bulb location changes. Electrons respond. The filament heats up. Photons are emitted, and you see light. All of it, every single step, is the electromagnetic field doing its thing. The field is real. The field is fundamental. The field is what matters. And that's what Feynman tried to tell us. That's what most people never really understand. Electricity is not what you imagine. It's something far stranger, far more beautiful, far more fundamental. It's not comfort. It's not familiarity. It's truth. But let me give you something concrete, something you can actually test, something that will prove to you that what I'm saying is real. Take two wires, long wires, run them parallel to each other, separated by a few centimeters, connect them to a battery at one end and a light bulb at the other, forming a long, narrow, rectangular loop. Let's say the wires are 100 meters long. Now calculate, if energy travels through the wires, it has to go 100 meters down one wire and 100 meters back up the other. That's 200 meters total. At the speed of light, that's about 670 nanoseconds. But if energy travels through the space between the wires, straight across the rectangle, it only has to travel a few centimeters. At the speed of light, that's less than a nanosecond. The difference is measurable. You can build this circuit. You can measure when the light turns on. And what you'll find is that the light turns on after the propagation delay for the energy traveling through the space between the wires, not through the wires themselves. This experiment has been done multiple times by multiple people. The results are always the same. Energy travels through the field, not through the conductor. Feynman knew about experiments like this. He used them to make his point. The standard circuit theory is useful. It gives you the right voltages and currents, but it completely misses where the energy is actually flowing. Now you might be thinking, okay, fine. The energy flows through the field, but does it really matter? If the equations work, who cares where the energy actually is? It matters. It matters for understanding. And it matters practically. Let me give you an example. High-speed digital circuits, computer chips, cell phones, anything operating at gigahertz frequencies. At those speeds, the wavelength of the electromagnetic signals becomes comparable to the size of the circuit. You can't ignore the field anymore. You can't pretend energy flows through the wires. You have to treat everything as electromagnetic wave propagation through transmission lines. Circuit designers have known this for decades. When you're designing a gigahertz circuit, you don't think about wires. You think about transmission lines, characteristic impedance, reflection coefficients, standing waves. You're designing structures to guide electromagnetic fields. The conductor is just there to define the geometry. The energy is in the field. This is why modern electronics look the way they do. All those weird shapes on a circuit board, those serpentine traces, those controlled impedance sections, they're all designed to manage the electromagnetic field, to minimize reflections, to maintain signal integrity, to ensure the field propagates correctly. If you tried to design a 5G phone using simple circuit theory, ignoring the field, it wouldn't work at all. The signal would reflect, distort, and die. You need to understand the field to make it work. And this brings us back to Feynman's point. Understanding what's really happening isn't just academic. It's not just philosophical, it's practical. If you want to build technology that works at the limits of what's possible, you need to understand reality, not a simplified model. Reality. Let's talk about one more thing, something that makes all of this even stranger. The self-energy of the electron. When an electron sits there in space, it has an electric field around it. That field extends out to infinity, getting weaker with distance, but never quite reaching zero. And that field has energy. You can calculate it. The energy density at any point is proportional to the square of the field strength. Integrate over all space, and you get the total energy of the field. Except there's a problem. When you do the integral, when you add up the energy from all points in space, you get infinity. The field gets stronger and stronger as you get closer to the electron. At the location of the electron itself, the field strength is infinite. So the energy is infinite. The electron just sitting there has infinite energy. That can't be right. Electrons have a finite mass. E equals mc squared. If the electron had infinite energy, it would have infinite mass, but it doesn't. It has a mass of about 9 times 10 to the negative 31 kilograms. Very small, very finite. So what's going on? Where does the infinity come from, and how do we get rid of it? This is the problem of the self-energy of the electron, and it plagued physics for decades. People tried different approaches. They tried to put a cutoff on the integral, saying the field can't be infinite right at the electron. There must be some minimum distance. But that was ad hoc, arbitrary. It worked mathematically, but it didn't make physical sense. Feynman encountered this problem when he was developing quantum electrodynamics, and he found a solution, sort of. He showed that you could absorb the infinity into the definition of the electron's mass. You say that the bare electron, the electron without its field, has some mass. Then you add the infinite self-energy. The total is infinite, but you never measure the bare mass. You only measure the total mass, the mass including the self-energy. And that total mass is what we call the electron mass. It's finite. 9 times 10 to the negative 31 kilograms. This process is called renormalization. You're literally renormalizing the mass, redefining it to absorb the infinity. It sounds like cheating. It sounds like you're sweeping the problem under the rug. And in a way you are, but it works. The predictions of QED after renormalization match experiments to incredible precision. The infinities cancel out in every measurable quantity. What's left is finite and correct. Feynman was never entirely comfortable with renormalization. He called it a dippy process. He thought there must be a better way, a more fundamental understanding that would eliminate the infinities from the start. But he never found it, and neither has anyone else. Renormalization is part of how we do quantum field theory. It's ugly, but it works, and it tells us something deep. It tells us that the electromagnetic field is not just a mathematical tool. It's a physical thing with physical energy, and that energy contributes to the mass of the electron. The electron's mass is not just the mass of a little point particle, it's the mass of the particle plus the energy of its electromagnetic field. They're inseparable. This is what Feynman meant when he said the field is real. The field has energy. The field has momentum. The field contributes to mass. The field is as real as anything else in physics. Now I want to circle back to something I mentioned earlier. The fact that electrical signals and wires are the same phenomenon as radio waves. This is not obvious. It seems like they're completely different things. Wires and circuits feel solid, mechanical, well-defined. Radio waves feel ephemeral, intangible, mysterious, but they're the same. Let me show you why. Take a simple radio antenna, a straight piece of wire. You feed an oscillating current into it. The current goes up and down the wire at some frequency, say 100 megahertz. As the current oscillates, it creates an oscillating magnetic field around the wire. The oscillating magnetic field creates an oscillating electric field. The oscillating electric field creates an oscillating magnetic field. Back and forth, back and forth. And here's the key. At some distance from the antenna, the coupling between the electric and magnetic fields becomes strong enough that they can sustain each other without the antenna. The fields detach. They propagate away as a self-sustaining electromagnetic wave, a radio wave. That wave carries energy. It propagates at the speed of light. It can travel across the room, across the city, across the planet. When it reaches another antenna, the oscillating electromagnetic field pushes electrons in that antenna back and forth. An oscillating current is induced. That current can be amplified and decoded, and you've transmitted information wirelessly. But now think about a wire carrying an alternating current. The current oscillates. It creates an oscillating magnetic field. That oscillating magnetic field creates an oscillating electric field. The fields propagate along the wire as an electromagnetic wave, a guided wave, constrained by the geometry of the wire, but fundamentally the same as a radio wave. Same physics, same Maxwell's equations, same electromagnetic field. The only difference is the boundary conditions. In free space, the electromagnetic wave spreads out in all directions. Along a wire, the wave is guided, confined, forced to follow the conductor. But it's still a wave. It's still the electromagnetic field propagating at nearly the speed of light. This is why transmission lines have characteristic impedance. It's not the resistance of the wire. It's the impedance of the electromagnetic wave propagating through the structure, the ratio of the electric field to the magnetic field. For a coaxial cable, it's typically 50 or 75 ohms. That's not the DC resistance, that's the wave. Impedance. If you mismatch the impedance, if you connect a 50 ohm cable to a 75 ohm load, the wave reflects. Part of it bounces back. You get standing waves, inefficient power transfer, signal distortion. Just like light reflecting off a surface when it encounters a change in refractive index. Same phenomenon. Wave reflection at an impedance discontinuity. Feynman understood all of this intuitively. He could look at a circuit and see the fields. He could visualize the electromagnetic waves propagating, reflecting, interfering, and he was frustrated that most people couldn't. Most people saw circuits as networks of resistors and capacitors and inductors. They saw currents and voltages. They didn't see the reality underneath, the fields, the waves, the energy flowing through space. And he spent a lot of time trying to teach people to see it his way, to visualize the fields, to think about what's really happening. Not because it would help them solve problems faster, but because it would give them a deeper understanding, a truer picture of reality. Let me give you one final example, one final demonstration of how strange electricity really is. You have two metal plates, parallel to each other, separated by a small gap. You connect them to a battery, Positive charge accumulates on one plate, negative charge on the other. An electric field forms between the plates. That's a capacitor. Now, where is the energy? The standard answer is the energy is in the electric field. The field between the plates has energy density proportional to the square of the field strength. Integrate over the volume, and you get the stored energy. That's correct, but here's the strange part. The energy is not in the metal plates. It's not in the charges. It's in the empty space between the plates. The charges on the plates create the field, but the energy is in the field itself, in the vacuum, in empty space. Think about that. You store energy in a capacitor. That energy is sitting in the gap between the plates. Not in the plates, in the gap, in emptiness. How is that possible? How can empty space contain energy? Because empty space is not empty. It's filled with the electromagnetic field, always, everywhere. The field is always there. When you charge a capacitor, you're not creating the field. You're changing its configuration. You're adding energy to it. And that energy is stored in the field, which exists in the space between the plates. This is the same reason light can propagate through a vacuum. Light is an electromagnetic wave. It's a disturbance in the electromagnetic field. The field is everywhere, even in a vacuum. So the disturbance can propagate through the vacuum. Light doesn't need a medium. It is the medium. Or rather, the electromagnetic field is the medium. Feynman thought this was one of the most important insights in all of physics. Empty space is not empty. It's filled with fields, quantum fields, the electromagnetic field, the electron field, all the other fields. Those fields are real. They have energy. They can be excited, creating particles. They can store energy, like in a capacitor. They can transport energy, like in a radio wave or an electrical circuit. Space is not an empty stage where particles perform. Space is an active participant. It's made of fields. And electricity, at its core, is about manipulating those fields, creating disturbances, guiding them, using them to do work. That's the reality. That's what's actually happening when you flip a light switch. And once you understand that, really understand it, you can never look at electricity the same way again. You're not moving electrons. You're shaping space-time itself. You're manipulating the fundamental quantum fields that make up reality. You're commanding nature at its deepest level. And that's what Feynman wanted people to know. That electricity is not mundane. It's not boring. It's not just a utility. Electricity is a window into the fundamental nature of the universe. It's proof that space is made of fields, that those fields are real and physical and can be controlled, that humans have learned to harness the quantum structure of reality to power our civilization. Every time you charge your phone, you're manipulating quantum fields. Every time you turn on a light, you're creating electromagnetic waves. Every time you send a text message, you're encoding information in oscillating fields and transmitting them across space at the speed of light. That's not magic. It's better than magic. It's real. It's physics. And it's absolutely extraordinary. That's what electricity really is. Not what most people imagine. Not the sanitized textbook version, the real thing. The quantum fields, the electromagnetic waves, the energy flowing through space, the reality that Feynman saw and spent his life trying to explain. And now you see it too.